In this question, we are given that the initial population of the yeast cells is 6,000 and it doubles after 4 hours. And we have to answer these three questions. So let's answer the first question. That is, we have to find an expression for the number of yeast cells after t hours, which is represented by the function p of t. So let's make a quick analysis of how we can determine this p of t function. Since the initial population is 6,000, I'm going to represent at t equal to 0 hours, the population that is p of 0 equals 6,000. And it doubles after 4 hours. So therefore, after 4 hours, that is when t equal to 4, which is represented as p of 4, and this equals the double of this one. I can write down this as 6,000 times 2 power 1. And after 8 hours, that is after an additional of another 4 hours, that is this gets double, that is p of 8, and this equals 6,000 times of 2 power 2. And after t equal to another 4 hours, that is when t equal to 12, we see that this population is p of 12, and this equals 6,000 times of 2 raised to the power of 3. So this is what we get for t equal to 0, 4, and 8. This is the number of 8 cells. Now we have to write down this in terms of expression as involving t. So we primarily focus only this exponents, that is 2 power 1, 2 power 2, and 2 power 3. We need to find a relation for this number, that is when t equal to 4, this number, this power is 1. Maybe we can write down this as this 1 equals 4 by 4. This is equal to 1. And similarly, we find a relation for this one, that is when t equal to 8, the power is 2, which means that is 8 by 4. This equals 2. And similarly, for the next one, this is 12, and here it is 3. So this 3 can be written as 12 by 4, and this equals 3. So every time we take this value 4 divide by 4, that is this t value. So here also we take the t value 8 and divide by 4, and here also we take the t value 12 and divide by 4, which means we can write down this as that is p of t. We write the function p of t equals 6,000 times of 2 raised to the power of t by 4. So this is the expression which determines the number of E cells after t hours. We now answer question 2, that is we have to determine the number of E cells after 9 hours. So for that we can use this function p of t, which represents the number of E cells after t hours. I'm going to utilize this. This is 6,000 times 2 raised to the power of t by 4. So we just have to plug in t equal to 9 into this function or into this population model. So therefore this becomes p of 9, and this equals 6,000 times of 2 raised to the power of 9 by 4. And this equals 6,000 times of 2 power 9 by 4 is 2.25. We can plug this value into the calculator, and when we do that we get approximately 28,540.97, and this when approximated to a whole number, we can say that this is approximately equivalent to 20,541 yeast cells. So this is the number of yeast cells after 9 hours. Let's answer question 3. So here we determine the rate at which the yeast cells is increasing at 9 hours. Basically, we have to determine p prime of 9, that is the derivative of the p of t at t equals 9. So let's see how to find this one. Let me copy this population model, that is p of t. This equals 6,000 times of 2 raised to the power of t by 4. And we have to find its derivative, that is p prime of t. and this equals, we can use the constant multiple rule. So we put this 6000 as it is, and we have to find the derivative of 2 raised to the power of t by 4. For that, we will understand this, how to find the derivative of exponents. That is, suppose if we have y equal to a raised to the power of x, then the derivative of this, that is y prime, and this equals a power x times of natural logarithm of a. So I'm going to use this rule to find the derivative of 2 raised to the power of t by 4. Let me put it over here. So as of now, we have 6000 times the derivative of 2 raised to the power of t by 4. According to this rule, I have to put a raised to the power of x. That is, I have to put the same quantity, that is 2 raised to the power of t by 4, multiplied with natural logarithm of a. That is, natural logarithm of a here is 2. And then we will also have to apply the chain rule to find the derivative of t by 4. The derivative of t by 4 with respect to time is t. I'm sorry, it is 1 by 4. So this is 1 by 4. So we will also have to multiply with 1 by 4 into this p of t. So finally, let's rewrite this as a single quantity. That is, we have 1 by 4 here, and this 6000 divided by 1 by 4 is, I'm sorry, when you multiply with 1 by 4 or we divide by 4, we get 1500. So this can be written as 1500 times of, we rewrite this. This is 1500 times of 2 raised to the power of t by 4 times of natural logarithm of 2. So this is the expression for the derivative of the p of t function, which represents the number of cells after t hours. Now we have to determine p prime of 9, which is we have to replace t by 9 into this model. So let's do that. So therefore this becomes p prime of 9. This equals 1500 times of 2 raised to the power of t by 4, which is 9 by 4, times of natural logarithm of 2. We can plug this into this calculator. Maybe I will just rewrite this as 1500 times of this 2 raised to the power of 9 by 4 is 9 by 4 is 2.25, and multiplied with natural logarithm of 2. So we put this expression into the calculator and we get approximately 4945.77. So when approximated to whole number, this is 4946 cells. Since this is a rate, we put the unit as cells per hour. Cells per hour. So we answered this question 3. That is, the rate at which the number of cells is increasing at 9 hours is 4946 cells per hour.